And in the last class, we were going to talk about optimizing loops. And as we were discussing that it is getting a little, boring and tiresome to work through this online mode. So I planned that we'll do something little different today. We will get into some actions. So uh, today I have planned that I will first talk about the loop optimization, including loop invariance and induction variables and workout example on that. And then we'll have a short break. And following that, there will be a short in-class assignment, right? Something that you will have to do in the class itself, during the class itself. You can do it using your notepad, or you can use a pen and paper. And before the class ends, you will have to mail me that solution. Only then it will be considered for grading. Do not complain that it was not announced earlier and you are not ready, because whatever we are going to talk today is primarily what will be in that assignment. So please stay tuned, listen carefully to the presentation so that you can do the assignment well. If you find that your friends are not online, you can ping them to be online, otherwise they'll miss out on the assignment. Any questions, friends? No questions. Good. Okay. I hope you can hear me, right?
Yes, sir.
Yes, sir.
Okay, good, good, good. So let's have some actions at least. Is the presentation visible?
Yes, sir.
Okay, good. So, as I mentioned, after having done all different optimizations and then doing, somewhat optimal register allocation, instruction scheduling, and all that, we are going back to the optimization phase again, which could be at the 3 address code, or it could be taken up at the assembly level as well, which will focus on the loops. Naturally, we all understand that loops are important for optimization, because even a small benefit in the body of the loop would have great consequences if we have, say, the loop running for a large number of times. So we will look at what is a loop. I mean, you know what is a loop, I'm sure, but we will look at a little bit of a algorithmic definition for that. And we will define what is loop invariant and how to optimize for that. And then we'll move on to what is known as induction variables. Again, you know what is induction variable, but we'll show that there are, besides the primary induction variable, which at least the determinate loops will have, you have a number of other hidden induction variables which can also be exploited. So in terms of the source language, the loops are designated by loop constructs: for, while, do, while, go to with jump back, and so on and so forth, though that is not very preferred. Now, to define a loop formally, particularly on the control flow graph, we define a dominator. Look at the bottom of the slide first. In a control flow graph, a dominator for a node N is a node D, such that any path from the entry of the CFG to N goes through D. So you have a node D in the CFG, and you have a node N in the CFG. If you trace any path from the first instruction, entry to the CFG, to N, that path must go through D. Now, obviously, there could be loops in between, and there could be multiple paths, if, else, etc. But if all paths from the entry of the CFG to N goes through D, then we say that D dominates N, right? So a loop is a back edge in the control flow graph, obviously, because you are looping, so you have to come back. So it's a back edge in the control flow graph from a node L to a node H that dominates L. So now we can see that our common notion of a loop is getting formally defined. Obviously, back edges you can determine very easily by doing a depth first traversal of the control flow graph. You really know that a back edge is what one which you have already traversed, a node that you have already seen. And then if, if there is a back edge from node L to node H, such that H dominates L, then you are saying that you are coming back. So it ensures, the domination ensures that to reach L, you must have crossed H, and then you are coming back to H again. So that is what the basic concept of a loop. And we call H as the header of the loop, because you can very easily understand that if there are multiple statements like L in the body of the loop, this will hold good for all of those statements, that H dominates those statements. So the loop itself consists of the nodes on a path from H to L. Right? There could be multiple paths. All of those are part of the loop. So it is often convenient to organize the code so that a loop can be identified with its header node. So header kind of is a, intuitively speaking, header kind of is a point where you enter the loop and then you keep on traversing within the loop with forward and backward edges. Now, given this, we define a predicate loop HL if line L is in the loop with header H. Right? So two conditions. One is it has to be a loop with H as the header, and L must belong to the loop, which means that H must be dominating L. Right? Now, we have noted earlier too that when loops are nested, then you can optimize the inner loops before the outer loops. And inner loops are, because inner loops are likely to be executed more often. And inner loops could move computation to the outer loop from which it is hoisted further. Let's see what does that mean. So this is the basic definition of a loop. Now we say a loop invariant is an expression whose value does not change throughout the loop. And just to highlight, I have qualified the loop invariant expression with saying that it is pure, in the sense that it does not have a side effect. You know, in general, that may not be true. If there is a side effect, then there are more things to be taken care of. But we are right now considering loop invariant, which are pure expressions. So they do not have any side effect. They are just expressions. And they do not change throughout the loop. Then we define a set of rules for the loop invariant, and in terms of these predicates. So what are the predicates? First predicate is invariance predicate rather. INV HP, where P is a pure expression and it is invariant in the loop H. If P is invariant in loop H, then this predicate is true, otherwise it is false. Const C clearly is a predicate which becomes true if C is const. Loop HL is an instruction at L belongs to or dominated by the loop header H. We have already defined that. And def LX, instruction at L defines, that is, writes to variable L, X. Right? So it is a definition for X within the at the instruction L. Right? So if that happens, then we say it is true, otherwise it is false. So we write the loop invariant rules in the antecedent consequence manner. On top is the antecedent, and on bottom of the line is the consequence, that if the antecedent is true, then the consequence will be true. So there are 4 rules. One is a constant rule, which is obvious that if there is a constant, const C, if this is true, then inf HC will be true. If there's a constant, then it is invariant within the loop. I mean, it's kind of a trivial statement, but it's required. Then we have out of loop definition. That is, if we have a definition of X at instruction L, def LX, and if L does not belong to the loop, that is, if loop HL is false, note the negation symbol here. So this will be true if L is not a part of the loop. Then X is invariant in the loop H. So this basically says that X is defined outside the loop. So when will that happen? How will you algorithmically decide it? Actually, this is, you can see, is the basic use of reaching definition. That is, you are saying that anything that reaches the definition of X is outside the loop, right? So that is why it's called out of loop definition, right? So these are R1 and R2 are the 2 fundamental rules to get invariant. Then you can have more invariants from this. One is if you have an invariant loop invariant S1 and another loop invariant S2, you can see the and. If both of these are true, then an arithmetic composition of S1 and S2 is also an invariant. So if, say, A is invariant, B is invariant, then A plus B is also invariant, or A multiplied by B is also invariant, which is the composition. And finally, the propagation, that which says that if I have an invariant in the loop and L is a statement, L is an instruction in the loop H, where L is a assignment of T from the invariant expression. So what is L? L is an assignment where P is being assigned to the variable T, right? So it is a definition. So P is invariant. This statement is inside the loop. Then I can say that T, the variable T, is invariant in the loop. Right? So this is quite obvious. So this is the propagation rule. So using our earlier DFA on reaching definition to find the basic definitions which are invariant, and then using composition and propagation, we can find loop invariants in a particular loop. Right? So once we find the loop invariant, we would like to take it out of the loop and put it, what we say is a pre-header. Pre-header may exist or may not exist in the control flow graph that you have. In either case, pre-header is a kind of a block or a group of statements which immediately dominates the loop header. So which basically says that you cannot get into the loop without crossing the pre-header. So if you have that, then your loop invariant computations can be moved to the pre-header in order, right? So that's the basic concept. So a very simple concept. But so we have a very simple code snippet, a loop invariant computing a loop where all elements of a 2-dimensional array A is set to 1. Just to keep it simple in terms of index management, I am visualizing the 2-dimensional array as a 1-dimensional array, because by row major, that's what you have. So the loop control goes from 0 to width times height, the width of the array and the height of the array, the number of columns and the number of rows. Right? So this is highlighted because width and height are in this computation. The width and height are, of course, not going to change. Right? So this is on left below. If you come down, left below is the loop. You have the loop index I set to 0. Then you start the loop. You compute. So after that, what will compute? You'll compute this product width times height into a temporary T1. And if I is, forget about, for right now, forget about this underscore 0, underscore 1 kind of stuff. Just think of them as I. We will just explain why we have them. So just in terms of the 3-address translation that we have seen, if we just flip this condition to make the control flow simple. So if I is greater than equal to T1, then you have already completed the task, so you exit. Otherwise, you do the task, which is, computing the actual location of AI by index time size, etc., and then getting the address of AI and making assignment. So we skip all those. We do I assigned I plus 1, and we go back. We keep on doing this. So this is the basic translation of this code. So you have a very, very simple loop, and that helps to illustrate this. Now, if you look into this code, width and height, you can very easily understand that there is no statement in the loop which is a reaching definition for width or for height. So the reaching definitions of width and height must be outside the loop. They must be coming from outside. So by the loop invariant rule 2 that we have seen, that is out of loop definition, we know that width is a loop invariant, so is height. Now, if we apply composition, rule 3, then width being constant, width being loop invariant, height being loop invariant, their product is also loop invariant, rule 3. And so if this expression width times height is loop invariant, then by rule 4 or propagation, we have T1 as loop invariant. So this whole thing is loop invariant, and the moment this becomes loop invariant, it becomes candidate for hoisting. And for hoisting, we see that we already have a pre-header, because if you consider this for loop, I assigned 0 is something which will do only once, which will necessarily do every time you enter this loop. And you cannot enter the loop without doing I assigned 0. So that satisfies the condition of the pre-header. So you already have that. So what we do is to hoist, we take this statement, instruction T1 assigned width times height, and hoist it to the pre-header. So we are hoisting it. Look at the right. We have hoisted to the pre-header, and rest of the loop remains same. And this is not going to affect your computation. Your computation is going to remain correct, remain the same as you have found this as an invariant. And it certainly saves you a whole lot of, because depending on width times height, you would have done so many multiplications, width times height, number of multiplications in the loop if you had the code in the left order. But with hoisting, you will do it only once. So you have a huge benefit in terms of doing this. Now, please keep this in mind that rule 4, the propagation rule, could be really far more complicated in general than just an assignment. For example, suppose we are doing something on a string, and for that, we need to, for example, you're searching an element in a C string, right? So what we'll have to do, you will start, if that string is str, you will start with str0 and compare with that element. If it is equal, it's fine. You have found it. If it is not equal, you'll go to the next element and so on. As you do that, this bound width times height, what it will be? You will have a propensity to write it as strlen str, right? So strlen str is a function call. Right? So by our rules, you will not identify strlen called to strlen with your string str to be an invariant. Right? In fact, you will have a whole bunch of code there where you will put that param and call and all that. Right? But if you, that is syntactically if you look at. Now, if you look at the semantics, naturally, since if you are just searching in that string, you are reading it, str is not going to change. And if str is not going to change, strlen str, that value is also not going to change. Right? And it's a huge benefit. I mean, much more than what you see here. And I'm just saying it from our experience of, code management in the company. We did come across a situation where the customer complained that the code is very, very slow in this part. I mean, way slow than their expectation. And we looked at everything and we didn't find anything which can be optimized. Till it hit us that there are a number of places where we traverse along a string to do some pure reading kind of operation, whereas the loop bound is set as strlen str for the length. So all that it needed is you just write a separate assignment for a variable len, which computes strlen for str, and use that in the loop bound. So what I'm showing here, the point I'm raising it is that what we are showing here, the actual examples could be far more complex than that, and there will be deeper consequences of that. So this will mean that we have to see that even in a function transformation, not only just a pure assignment, but even in a function transformation, there could be loop invariant if from one computation of the function to the next, the parameters don't change and there is no side effect. Right? So that is a context that we are talking of. So having done this, let us move on to the next slide. So this was the first type of optimization that you can do, which is loop invariant, which is significant. And it does give a lot of benefit. But there's another which we can benefit from, which is induction variables. And I mentioned that even though usually a loop like what we have just seen, there is a primary induction variable, here it is I, but there are a number of hidden induction variables. So that primary induction variable is known as a basic induction variable. So formally we define that an induction variable is one which changes by a constant each time you go around the loop. So if I go back to the earlier slide, 12.7, I is an induction variable because I do I assigned I plus 1. So I is changing by 1 every time. Right? So that is an induction variable, we all understand. Now, based on this, we define a derived induction variable which has the form A star I plus B, where I is an induction variable and A and B are loop invariants. So what will happen if I is an induction variable, it changes by a constant? That is the basic induction variable. Or it could be a derived induction variable itself. Now, if A and B are loop invariant, they don't change as you iterate. So what will happen? If I changes by a constant, then A star I plus B will also change by a constant. So if I changes every time by, say, an amount, a constant C, then A star I plus B will change by A star C. A being loop invariant and C being a constant, it is also a constant change as you go around the loop. Right? So those kind of induction variables are known as derived induction variable. Right? Now you will get a justification for why we are doing this underscore annotation. We try to define or try to identify the induction variable in three ways. One is the induction variable where it gets the initial value, which will happen in the pre-header. So to mark that, we mark it as if at I0, I underscore 0. So it is in the pre-header before the entry to the loop. The current value of iteration is I1, I underscore 1. Naturally, it is set from I0. And I2 is the value of the induction variable in the next iteration. So as you traverse the back edge and come back to the header of the loop, you will set I2 to I1. Right? We are just, it's the same variable, but you remember, we did some kind of, while we were discussing about registers and, optimization in the graph, we came across similar concepts where we were, for the same variable, we were separating out lifetimes by assigning different variable names to them. Here we are trying to do something similar. Is the same variable I, but based on its involvement in the pre-header initialization, or in the current iteration, or in the next iteration, we mark it as different variables. Naturally, in the next iteration, it becomes the then current iteration, and we don't need to keep on defining I3, I4 like that. We can just manage with this. So now let us go back now let us take a new code. So this is, we are trying to define a function is sorted, which takes an array at an integer number n. Naturally, the array stores a set of integers. So, and n is a value which designates how many elements are there in the array A. Naturally, the preconditions, or the, so to say, the invariants here are that the predicates are n will have to be greater than equal to 0, otherwise it's not defined, and n will have to be less than equal to the length of A, that is the number of maximum size that is added. Then what we want to find, that if the array A is already sorted, right, and we are looking for being sorted in the increasing order. Okay? So in terms of computing this, we just go over the array, and every time we check if AI is greater than AI plus 1. If it is sorted in the increasing order, we will find no AI and AI plus 1 where this is true. So if we find 1, then we return false. But if the loop goes through without any such pair being found, then we come out of the loop and return true. That is the is sorted function. So that is translated here. So I assigned 0, T0 assigned n minus 1. Again, I less than n minus 1 condition is flipped for control simplicity, which will have through optimization. So if I is greater than equal to T0, you come to this return 1. Otherwise, you continue. So you have to compute AI, which is 4 star I into T1. T2 is A plus T1. So you can see here that we are doing a little bit of a trick. And the reason we do that will become clear as we go to the optimization later. Is instead of writing it as A T1, A within square bracket T1, rather we are writing it as if as a pointer. Okay. So we are trying to separate out from the high level array A and the actual byte memory array, which we call M. So M is a byte array in the memory. So we compute the A is the base address, T1 is the offset. So I add T1 to A to get the pointer to the particular starting byte of this AI, and put it to T2, and then use the memory array referencing to get the value of MT2, which is basically AI in the high level in T3. And then we compute I plus 1 in T4 do the same thing, compute the offset, add to the base, and get T7 as AI plus 1. Right, so this is the basic translation. I know you all are very familiar with all this. I just wanted to walk through because of the difference in the way of using a pointer type of computation here in A plus T1 or A plus T5. And then you compare T3 with T7, AI with AI plus 1. If it is greater, you jump to false and you return 0. Otherwise, you come to the last expression for the for loop, do I assigned I plus 1 and go back to the loop. Right? Again, everything is annotated here with 0, 1, and 2 to distinguish the distinct values of I in the pre-header, in the current iteration, and in the next iteration. Now, if you look into this now with a different set of classes as we are trying to optimize. So pre-header, we know I is a basic induction variable, we understand. So loop is on I. So it's a basic induction variable. Now, what is T1? T1 is 4 star I. So we observe that if I have a basic induction variable I, and if we have A star I plus B, where A is a loop invariant, B is a loop invariant, then that is a derived induction variable. Here, obviously, 4 is a constant, so it is a loop invariant. B is 0, it's a loop constant loop invariant, so this is a derived induction variable. Similarly, T4 is I plus 1. So that also is a derived induction variable with I being 0 and B being 1. Right? So we can see that, as I was saying, that there's one primary basic induction variable, but there are hidden ones. So now let's move on and try to use this information. Now, first, let us consider T4. What do we see in T4? We see that there is a common sub-expression. T4 is I plus 1 and I2 is also I plus 1. That is I1 plus 1, I1 plus 1. So there's a common sub-expression. So we can eliminate that. Now, what we want is if we eliminate, then what will happen? Actually, by our earlier strategy, what will happen is we will set by common sub-expression, we'll say T4 is already defined as I plus 1, so I2 can be set as T4. But here, we play a little smart with the basic induction variable. We do not do that. We don't touch the update of the basic induction variable. So we want to do the sub-expression elimination in the other way. That we say that first we have this, and then we will update T4. Now, this is when you will realize the value of or the importance of marking the next iteration value for I, because I2 is a variable which is the value of the basic induction variable in the next iteration. So in this iteration, it is not used at all. So it does not matter as to where in this loop I actually compute I2. So what I do is I hoist it or I move this code before T4. So I move it before T4. And it does not change anything. It cannot, because I2 is defined only once. It will be defined only once. So it cannot, I mean, I don't even need expensive tests to be done. I just move it before T4 and here, and then I do the common sub-expression elimination. So it is the same thing happening, but it's just that what is the primary variable that is being defined by the common sub-expression and what is the variable that is using its value. So now I2 does not, expression of I2 does not get disturbed, which we do not want to touch. But T4 now gets the value of I2, right? So this is simple. I mean, you can see all the previous things we are using, but maybe in a little tuned way. So this is the code we have. Let's go to the next slide. Please stop me if you are finding any inconsistency or difficulty in understanding. Otherwise, as such, I think these are simple to do. Okay, so this is what we have from the last slide. So now we look at the derived induction variable T1, which is 4 star I1. Right. Now, as we are going through this loop, we have to find out how can we compute T1 in the next iteration from the T1 that we have in the current iteration, right? Because it is a derived induction variable, so it changes by a constant. So formally what we do is we introduce a new induction variable G, right, which will denote what is T1 here. So we introduce J. So what is J? J will stand for 4 star I. Right? So what happens if I introduce J? I will need the initialization of J in the pre-header. So J0 is 4 star I0 because J I'm introducing as 4 star I. So I have that here. And when I2 is updated with I1 plus 1, naturally, my J2 will also need an update. So it is J2 becomes 4 star I2. The new computation with I2 will be required. So I push that code here. And in T1, instead of computing 4 star I actually put J1, my new induction variable assert, right? So I have a new induction variable now, right? Okay, so let's move to the next one. Now, let us see what are the things that we have. J is 4 star I, right? When the level is stable. So what is J2? J2 is 4 star I2. What is I2? I2 is I plus 1. So it's basically 4 star I plus 4, or rather 4 star I1 plus 4. Now what is 4 star I1? 4 star I1 is J1. So it's basically J plus 4. And I further observe that in the pre-header, 4 star I0 is actually 0 since I0 is 0. So I apply those two. Apply J0 is 0 here. And we had this. So J2 getting 4 star I2 becomes J2 gets J1 plus 4. Right? So this is how I have optimized the new variable, new induction variable J. Let's move on. Now we can do some copy propagation and loop invariance. For example, here I see that T0 getting n minus 1 is a loop invariant as well. So I move it to the pre-header. I've moved that. Now T1 is set as J1 and T2 is set as A plus T1. So I can do a copy propagation. So I make it T1. I make it T2, I make it A plus J1. And with that, T1 has no purpose. So I remove that dead code is eliminated. Now, in the same way, T4 is I2. So if I propagate, it becomes 4 times I2. So I make it 4 times I2 and I eliminate T4 as well. Okay? So this is all this we have seen with the new variable. We are able to remove these temporaries. Let's go to next. We now have that here we have 4 star I2. Okay? Now, what is 4 star I2? 4 star I2 is basically J2. Okay? This is a smarter common sub expression. using the assertion that J2 is 4 star I2, which is not explicit in this code, but we have that assertion already because that is how we have created J. Right? So 4 star I2 becomes J2 and we propagate that, right? Propagate T5. So T5 becomes J2 and we propagate that. So here we have A plus J2 and get rid of T5. Right? Next. Now we can see that there is yet another induction variable. What is that induction variable? That is A plus J1. This is a derived induction variable. Why A plus J1 is an induction variable? Because in A plus J1, in the basic definition of a derived induction variable, that if I is an induction variable, a and small b are loop invariants, then A star I plus b is a derived induction variable we have seen. So J1 here or J here is an induction variable. So if you set small a as 1 and small b as capital A, the base address, which obviously is loop invariant, then we know that A plus J1 is a loop invariant. Right? So like before, we give it a new name. We call it K. So K is A plus J1. So K0 is A plus J0, which I put in the pre-header. And this is A plus J1 is K1. And I have to update K2 as A plus J2. I have to update K2 as A plus J2. A plus J2. A plus J2 is A plus J1 plus 4 using the assertion of J2. Now A plus J1 is K1. So it is K1 plus 4. So I write it here as K1 plus 4. I insert this code. Right? So I also get the invariance that K2 is A plus J2 at this point. Right? All true. Let's move on. Let's. This is what we had. Now J0 is 0. So I propagate that constant. So I get K0 is not A plus J0, but simply A. T2 is K1. So I do a copy propagation. I get T3 is MK1. T6 is K2. So I propagate that copy. I get T7 as MK2. And we have been able to simplify the code significantly. Right? So at this point, you may start thinking, well, we may possibly be done, but we are not. Look at this code on left. You have 3 induction variables now, I, J, and K, being independently updated. Right? Now, if you look at I, it is used here in this test. If you look at K, it is used here in T3, in T7, and subsequently in the condition check. But look at J. J is initialized here. It is updated here, but is not used anywhere. Right? So this we define as a new, DFA called neededness analysis. That is, here is a computation which exists, which is correct, but is actually not needed. I mean, you compute something which is neither a primary program defined variable nor is used anywhere else. Right? So it is similar to liveness and diffuse analysis. It's called neededness, that J is computed but is not needed anywhere. Right? So with that, I can eliminate J. So J is not needed anymore. And I'm down to only 2 induction variables now. And you would tend to think that, well, we must be done, right? Okay. So let's see that I1 is still needed, or I is still needed, and it is used only at one place. That is this if condition governs the conditional jump. So let's look at this condition more closely. I1 is greater than equal to T0. Right? So we do a trick of converting this comparison in the form of a derived induction variable. Why? What is the motivation for doing that? My other induction variable is K. My other induction variable is K, which is actually A plus 4 times I. So what I do, I multiply this both sides of this comparison by 4 and add A to both sides. Right? Now, as we do that, this left-hand side of this comparison becomes K1. Right-hand side is A plus 4 star T0. Right? It doesn't look like the 3 address code anymore. Don't worry about that. That can also always be taken care of by introducing some more temporaries. But the key thing is we want to get rid of I1, and we have been able to transform I1 into K1. After having done this, if we see now in this, you have the I assigned 0 and I assigned I plus 1. I is no more used in any other quad. So it has no further use. Right? So I can, by neededness, I can get rid of I. I'll get rid of I. I also observe that A plus 4 star T0 is a loop invariant, because T0 I already have as a loop invariant. So by combination, 4 star T0 is loop invariant. Again, A is a loop invariant. It's a constant. So A plus 4 star T0 is a loop invariant. So this whole thing is a loop invariant. So I introduce this computation in the header. So I'm again hoisting this part of the expression. So T8 is 4 star T0, a loop invariant. T9 is A plus T8, a loop invariant. And I use that T9 here. Right? So now I have got rid of the original induction variable I, the other derived induction variable J. My whole thing is now only in terms of the induction variable K. Right? So this is, as of now, the final code. So now if you actually think, what we have got is something very, very, simple. If you had written, instead of writing AI and AI plus 1, if you would have written it in terms of pointers, the array, if in terms of pointers, you would have actually written something like this, that, you start with the base address, which is A0, right? And you update every time by an offset 4, which is the size of int, which gives you A1. Then from A1, you get A2. From A2, you get A3, and so on. And every time you have to check with the bound of the array. The bound of the array is being computed here by n-1, 4 star, n-1, A plus n-1. That's the last pointer index you have. So that is in terms of the range, that is the closing of the range. So you compute with that. And if you are within the range, then you simply access the memory array. And at K and at K plus 1, right? You don't need to. So you had a K plus 1 there, and you are, or rather a I plus 1 there, which is now become K plus 4. And you, as it is, need K plus 4. So the same computation is not needed twice as is working out here. And you use that K2, you have the 2 values. So you can see that probably by smart thinking, you could have written this code directly, but through all these transformations, we have actually been able to reach to this optimization point. So looks nice. If you think that this is done, then you can try out that there's more that can be. There is still redundancy. For example, if you look at here, so what I'll take in T3, T7. T3 initially is A0, T7 is A1. Then T3 is A1, T7 is A2. Then T3 is A2, T7 is A3, right? So you can see that this access is happening twice after the first element, first indexed element. The subsequent ones are happening twice, once in an iteration, and then in the next iteration. Right? So I can optimize this by what is known as unrolling the loop. That is, instead of doing it for one iteration, if we do two iterations one after the other, two iterations of the body one after the other, then we will be able to use T7 as T3. Okay? So that unrolling we can do in situ, or the unrolling we can do by, as I come back, I can set T7 to T3. If we want to do that, I'm sorry, T7 to T3. If we want to do that, then you have to make sure that at the entry, the condition is satisfied. So there is some more work to be done, but I can do that. So I can hoist T7, initial value of T7 is A, which is K0. So I can have that hoisted here, and then again used here. So T3 can take the value of T7, and T7 every time is freshly computed. So he will do that indexing only once in the array. So there could be more in this. So this is all about the loop based optimization, which is where primarily we have used the earlier optimizations of peephole, GSE, global common sub expression, and then we are primarily using two optimizations. One is loop invariance, and the other is induction variables. Right? So let me stop here and see if you have questions. Yes, friend.
Sir, could you please open the slide of the unoptimized example of the second code, the unoptimized version?
The very first one.
Yes, sir.
Actually, you don't need to see me, so I'll be on the slide. You just tell me where to go. Right? So I'm back. You mean this one?
So the unoptimized version. Yes,
this is unoptimized. This is the first raw code that you get.
Yes, sir.
Yes.
Yes, sir. So, sir, we have I0 is equal to 0 in the pre-header, and then right after in the loop body we have I1 greater than equal to T0. So when is I1 initialized?
You can consider it is happening. See, this is symbolic. Please understand, this is symbolic. At the end, it is not a different variable. Right.
Oh, I see.
Right. So at the end, it is not unless you distinguish the value of I in the current iteration and in the next iteration, you are not able to see the process of induction. And unless you can see the process of induction in a variable, you cannot see the process of induction in variables which are derived from it. Right. So you can, here it is more symbolic. Even in the final code, if I'll come back to this again, but let's say in the final code, if I see here, K0, K1, K2 has no meaning. You call it K. The code actually is with K. So these are annotators to tell us that what value of k is being used. For example, here if I have k and if I have k, here I have k assigned k plus 4, then mk and mk here, are they common sub-expressions? We have to do analysis and say
No.
no, k is getting updated. So it is extremely difficult to see that the mk here in T7 is a common sub-expression for mk here in T3. Right. By doing this annotation, it makes it easier for you to visualize that and do that, algorithmic process. Otherwise, if you look through entire of this code that I have discussed, at any point of time, for example, take anywhere in the middle, anywhere here, you can just replace I0, I1, I2 by I, J0, J1, J2 by J, and so on. And if you want a correctness in terms of these, annotated variables, then all that you need to do is when you are saying that go to loop I0, J0, which is we are saying that you're starting it first. At this point, you can set that I1 is I0, J1 is J0. And when you are doing go to loop I2, J2, at this point, you can have I1 assigned I2, J1 assigned J2. Right? Those are, that you find, this is a visualization. This is a computation visualization issue. You'll have to think little beyond just the code that you read. We are maintaining this.
So, sir, yes, each version is assigned exactly once.
Yeah, okay. Yes.
Like I1 corresponds to exactly one thing and I2 corresponds to
exactly. That is, so you identify. This is the critical thing. This is the critical understanding, this definition. You identify that an induction variable has exactly 3 roles. One in the pre-header when it is initialized, one in the current. If your induction variable changes in the current iteration, it is not an induction variable, and this analysis cannot be applied. Induction variable is an invariant for one iteration. So that is the second role. And the third role is based on the induction variable value in the current iteration, what is the value of it in the next iteration? So the I0 happens only once, I1 and I2 keeps on alternating. This, when the people who did formulated this analysis technique, this at least I feel is a very significant and simple contribution to visualize iterations. Otherwise, you'll have to visualize by unfolding it. It becomes an infinite control flow graph. Then you'll be able to see all this. But that's in a compact form. This annotation is helping you to do that. Right. And the same concept is used for J. Same concept is used for K, and so on. Right?
Yes, sir.
Any other questions, friends? Any other question or doubt? Is this clear? Okay. So, as I said, we will have an in-class assignment now. You can take a break, because it's all your time. Right? And it's in-class assignment. It is certainly open book. I'm not expecting you to follow any protocol. It is open book. So please go to the internet and consult if you need to, because my only objective is you learn this very important and consolidated optimization technique. And obviously consult your friends across, because in that way you learn. But I mean, be informed that when when you help your friend will also get credit for which you are actually responsible. But that is your choice. You are always encouraged to help your friend. And I'm not going to check at all as to if the solutions from two people are same or not, because this is a workout problem. So the solutions would significantly be same. All that I want is all of you are able to do this and send me the solution by 9:55. It is 9:11 now. So I suggest that you take 2-3 minutes break, and then if you're comfortable, take a pen and paper, solve on that, take a photo and mail me. If you are comfortable working on the system, because this is all just writing code and transformations. So once you have done the 3 address code, everything else would be very similar. You can do it on the system, make it into a file, and send me that. So let me put the assignment in place before we go to the break and start this process. Here is a slide that I did not discuss, slide 22, where I've shown, actually you can read it at your leisure, that for the code that you have worked on, if you just give it to Visual C++, what does it do when you don't optimize? So it keeps everything, and when you optimize, how does it do this loop optimization, and you'll be able to see the treatment of induction variables in the code. You can read it for yourself. Now, this is a simple assignment that you have. There is a code segment. Just for clarity, I have given the declaration statements. You'll not have to deal anything with that. We are just interested in this for loop where I goes from 0 to n, and A is assigned B plus C, and then Pi is assigned A star A plus 4 star I. Very simple statements. And the assumption is size of int is 4. So what you need to do is to generate the TSC, draw the CFG, do standard optimizations. Obviously, I'm not expecting you to run the formal DFA. You will just mark that this is, kind of what you can do is just show the changes that are happening because of this. You can do it by observation, but have to do it carefully. Then once the usual ones are optimizations are done, then you optimize with loop invariant and induction variable. This is what is critical. And this is what we are really trying to see that you have learned. And mind you, when you do this, you have to ensure correctness of your optimized code. Right? I'm telling you, there is a small, caveat which intentionally I did not point out to you, because I know you all are smart people. So unless you take care of that caveat, then you'll be able to optimize and all that. But for some values of some variables, your code may give a wrong result compared to the original. So take care of that. Write your solution, send it to me. Obviously, mention your name and roll number. Right? And what I forgot to write here, please write the subject header. Please write in-class assignment as a subject header and nothing else. Right? Please follow that. Don't keep a blank subject or some other subject. The reason I'm saying this is I'll be getting 80, 90 mails on this. So I'm going to use a rule in my email client to capture them all in a single folder. So if you write different subjects, I'll not be able to do that. Right? So please just write this in the exact way. Okay? Any questions, friends, on the assignment? And the marks will be 10. You'll get 10 marks for that as an assignment. Professor Mitra will take care of that. Any questions?
Sir, do we have to submit it handwritten or we can submit it typed as well?
This is given. You may write your solution on notepad or on paper. Anything. You can write it on paper and just take photographs, just take snaps with your mobile phone, put them in a PDF file and send me. Or, I mean, I'm saying PDF file because if you send multiple images, it becomes difficult for me to understand what is first and what is second. Or you can do it in a notepad, anything, Word, any document. You must work out and show the solution. Any other question? No. Okay. So good. So we'll have a break for a couple of minutes. What I mean is I will have a break for a couple of minutes. Your break is your choice. So it is 9:15 now. From 9:20, again, I'll be available on my microphone, though I don't expect much of queries from you, but feel free to ask if you have anything. And so you have 40 minutes till 9:55. Don't target for 10 because we are going to close at 10. So target for 9:55 and submit it. Okay. Okay. Go ahead. Start doing. একটা পার্ট হিসেবে হয়ে যাবে আরেকটা অ্যাসাইনমেন্ট আমরা ল্যাবে ডিসকাস করেছি এটা হ্যাঁ কিচ্ছু হচ্ছে না হ্যাঁ সেটা তো তাদের তাদের যে রিটার্ন করছে সেটা তো কোনো মানে থাকছে না পরে গিয়ে তো কেউ ফেলে দেবে তারপরে কি কেমন বলতো সবাই তখন নিজেদের একটা স্ক্রিনিং করতে লাগবে এইসব করতে হবে তারপর বাবা লিখতে করো আড়াই বছর
जैसे तेरे को उठाया वैसा उसको उठाऊंगा ना, परमानेंट बात करना तो बंद होना श्योर है वो टाइम।
Yes, what is the doubt? Did somebody ask anything?
No, sir. I think someone's mic got unmuted.
Okay. That's it.